Hello everyone, and welcome to the flat holography parallel session. Our first speaker is Sangmin Choi, who's going to discuss asymptotic symmetries and log-soft theorems.
Right, thank you. I want to thank the organizers first for giving me this opportunity to talk about my work. I'll be talking about the relationship between asymptotic symmetries and something called the log-soft theorems. This is based on a work that we put out, my collaborators and I put out early this year, and something that we are still working on, and we want to put the another paper out hopefully within the next few weeks. So I'll begin. So soft theorem. What is a soft theorem? It's a statement in QFT that derives from studying Feynman diagrams. So you have in gauge theory an amplitude with an external soft photon or graviton. You take the limit as the energy goes to 0, and you have a factorization of the amplitude times something called the soft factor. There's a leading term that is divergent in the soft energy scale and diverges. And then a follow-up is an independent term that is convergent. So this is the soft theorem. And then asymptotic symmetries. What is an asymptotic symmetry? The quickest way to see this is you think of all the allowed gauge symmetries of the theory, and you mod it out by the redundancies, the trivial gauge symmetries. Of course, this is not the most general way to see this. But still, this is a useful way of thinking about this topic. Now, you could ask, aren't all gauge transformations trivial or redundancies? The answer to this is no. If you follow the Noether procedure to compute the generators of these gauge transformations, you notice that there's a step where you impose a fall-off condition on the parameter for the symmetry to be trivial. Now, the transformations that do not obey this fall-off condition turn out to be physical. Just to sort out the terminology, this asymptotic symmetry group is often referred to as the large gauge transformations. This term has been used before in the context of non-abelian gauge theories and so on. But this definition allows for even the topologically trivial large gauge transformations. In some literature, this is referred to also as the improper gauge transformations. So let's look at an example. In QED, the asymptotic symmetry is the set of all U1 gauge transformations whose gauge parameter does not vanish at infinity. Now, if you compute the generators using this condition, then you find that they do not vanish on shell. They have a non-trivial action on the states, and therefore these are physical transformations. Now, the asymptotic symmetries turn out to be symmetries of the S matrix. So what that means is if we compute the commutator between the scattering matrix and the generators of these transformations, and then sandwich them between in and out states, then this turns out to be 0. And this equation is called the Ward identity of the asymptotic symmetry generators. Now you could ask, well, we have a bunch of these asymptotic symmetries, and they seem to constrain the amplitude even more than we thought. So what are these constraints? It turns out that these are not new constraints being acted on the amplitudes, but rather these are just a clever rewriting of soft theorems. So this equation here, if you write down all the variables and then do some rewritings, you can write them as the Weinberg soft theorems or subleading soft theorems and so on. So in QED, the large gauge transformations, whose parameter is convergent, turns out to have Ward identities that correspond to the leading soft photon theorem. In gravity, we have the BMS supertranslations, whose Ward identity turns out to be the leading soft graviton theorem. This goes on. If you consider gauge transformations in QED that are divergent in large distances, then its Ward identity corresponds to the tree-level subleading soft photon theorem. In gravity, the counterpart is BMS superrotations. Its Ward identity is the subleading soft graviton theorem at tree level. This correspondence turns out to be quite general. It's worked out in the literature case by case, but this extends to higher dimensions. It extends to theories with supersymmetry, and so on. Now, in this talk, we will look at this particular case where we look at large gauge transformations in QED whose parameter is divergent. Its word identity is the tree-level subleading soft photon theorem. We will extend this correspondence to loop order. So let's first review what happens at tree level. We consider in, say, scalar QED for definiteness, a gauge transformation where the parameter is of order r, where r is the radius from the origin. Now, if we impose the Lorentz gauge condition to this parameter, this condition dictates the form of this parameter in the large R expansion. So at leading order, there's a term that's linear in R. Its coefficient is independent of time. The next one up is linear in time, and this list goes on. Now, if we take this gauge transformation and use covariant phase space formalism to compute the generator, this divergent piece gives us a term that is linear in time. And as we take time to infinity, we should regulate this divergence. And then there's a term that is finite. It turns out that even though the charge is formally divergent, we don't really have to worry about this divergence because the coefficient turns out to be the generator of a convergent large gauge transformation, whose charge is conserved by itself. It's associated to the leading soft photon theorem. So the Ward identity computed from this divergent charge, we only have to worry about this finite piece. And it turns out that the Ward identity is exactly the tree-level subleading soft photon theorem. So this is what happens at tree level. The subleading soft theorems receive corrections at loop order. This is well known from the computation of Swinburne and his collaborators about a decade ago. What happens is that as you take the soft energy to 0, we have the leading soft vector, the finite subleading soft vector, and then a correction to the subleading soft vector. So it looks like the soft vector is divergent, so is the soft theorem ill-defined. Now, the answer to this came a couple years later by Ashok Sen and Biswajit Sahu, where actually, if you look at the loop diagrams carefully, without taking the soft energies to 0 first, then you find a term that is in between the leading and leading soft vectors. There's a term that is non-analytic in the soft energy omega that goes like log. And this gives you a new soft theorem that is often referred to as the logarithmic soft theorem. And here's what the logarithmic soft vector looks like. If you recall what the leading and subleading soft vectors look like, you'll find that this is way more complicated than the other terms. And now we have a new soft theorem, the logarithmic soft theorem. So the natural question to ask is, what is the associated asymptotic symmetry? Okay, so to answer this question, we will work with massive scalar QED. Since we have massive charges and massless photons, we use two coordinate systems. One for the time like infinity, where all the massive charges go to at infinity. So this hyperbolic coordinates are designed such that at infinite tau, the momentum, the asymptotic momentum of the charged particles fix a point rho and zz bar that the particles end up at. For the massless particles near scry, we employ the usual retarded coordinates ur, c, and z bar, where u is the retarded time. And this works such that at r goes to infinity, the trajectory of the massless particles end up at the point on the scry. So this is the setup. For the asymptotic symmetry, we look at the same symmetry that corresponded to the soft theorem at tree level. So this is the divergent large gauge transformations. The parameter is linear in R. It satisfies the Lorentz condition. We have massive charges now, so we should look at the counterpart of this transformation at time like infinity. So the parameter turns out to be linear in tau, and then subleading terms vanish at infinite tau. Of course, these two parameters should match smoothly as we move from time like infinity to the future boundary of Scri, and these can be mapped by the Euclidean ADS3 bulk to boundary propagator that was worked out a decade ago. This asymptotic symmetry is not new. This is completely what you'd expect from the tree level subleading soft theorem. The new thing is that we now don't work with free fields, but we take long range interactions into account. So usually what you'd do is that at large times you don't have interactions, so you solve the Klein-Gordon equation for the massive charges. But actually, the gauge field, the radiative gauge field, doesn't propagate to time like infinity, but the presence of matter sources a Coulombic field that goes like 1 over tau for the gauge field, and this gives rise to this additional term due to interactions. And if you solve this equation, what you find is that the large time asymptotic of the massive field is not just the free field, but it acquires an infinite phase. Now this infinite phase, this equation only holds at large, the leading order in large tau, so you should think of this phase not as an exponential, but rather 1 plus IE log tau times this gauge field. And there's subleading corrections that go like 1 over tau to the 5/2 and so on. Okay, so this fact motivates us to use the following ansatz. We have the B naught log term that goes like the phase. We have a B naught term that corresponds to the free data, and then we have more corrections following up, each with one possible factor of log tau. We plug this into the equation of motion and solve it, and what we find is that all these B naught log, B1 logs, B1, B2, all these other coefficients can be written in terms of a single coefficient B naught, and there's nothing that constrains B naught. So B naught is the free parameter, everything else is determined in terms of B naught. We use the covariant phase space analysis using this asymptotic form, and what we find is that the phase space itself is divergent at large time. So we should regulate this by introducing an infrared cutoff scale, lambda. And if we compute the charge at time like infinity, this gives us the hard charge that goes like log of the infrared scale. Now, just as in tree level, we have a term that is overleading to this, that is linear in the scale. But we are not worried about this term because the coefficient turns out to be exactly the leading charge that is conserved by itself. So as far as the conservation of this hard charge goes, we only have to worry about the subleading terms, which is still divergent, by the way. Now, if you look at the expression, this actually turns out to be the hard part of a logarithmic charge that was proposed by Alok Lada and Miguel Campiglia 5 years ago, whose Ward identity is exactly the Sensahu log-soft photon theorem. So this is the massive charge side of the story. Next, we turn to the soft side. The game changer on the hard side was interactions. So here, the story is the same. Interactions give rise to logarithmic terms in the large R expansion of the field strength and the gauge field. I've highlighted in red the terms that appear due to this long-range interactions that you would not have had in free theory. Not only that, because we have to match the asymptotics at the infinite u asymptotics has to match with the infinite rho asymptotics of the time like infinity, we have additional terms that come up in the large U expansion. So I've listed some things here. This term that goes like 1 over u on the gauge field will have a critical role in this story. Now, we have a bunch of fall-offs. We can, again, consider the divergent large gauge transformation. So we have a symmetry, we have the fall-offs. We run the mill of covariant phase space formalism to compute the charge. What we find is that there's a linear term, again, that is divergent, but we don't have to worry about this because this is conserved by itself. We don't have a log term. We seem to have something that looks finite. And this expression actually is exactly the same as what you'd expect from free theory. If you have computed everything without these red terms, you'd still get this expression. So it looks like on paper, the log term is missing on the soft side of the story. So has anything changed? Now actually, because of this new 1 over u term here, this u integral is formally divergent. So what we have to do is we have to again introduce a large time cutoff to cut out the corners of scry and then regulate this. And using this, we can pull out the infinite piece in this soft charge that is hiding in this expression. And if we do so, what we find is that we again have a term that goes like log of the infrared scale. The coefficient looks like this. And this expression appeared back a couple years back in the Miguel Campiglia and Alocada's paper, where they proposed the logarithmic soft charge whose water identity gives you the log soft theorem.
So
now, yes?
What is A0A?
Oh, yes. The 0 here refers to, if you take the A of A and do the large R expansion, this is the leading term that is independent in R.
So,
So-
could you finish?
Yeah, I mean, can you show again?
Yes.
This expansion of
Yes. So this is this term here.
Right, and so, but it was, so the diverging part was proportional to this guy. Yeah?
Yes.
And how then does it?
Oh, how
Does it come back to this A0A again?
A0A, yes.
Yeah. How do you go from the I mean, what the last equality? How does it work? Yeah, that last equality.
Yes. So this u del u here picks out this term because the derivative kills the leading term. And then you can, if you do this integral, where you don't go from negative infinity to infinity, but rather you go from the lambda inverse. So you carve out the infinities of scry, then you get a term that is divergent as you remove this lambda. And if you have just done this integral with infinities, then you'd have gotten an infinity. But we are trying to regulate that and see how it goes as we remove the infrared regulator. And this leading term can be rewritten in this form with different projectors. So here we have the u del u, but now we have another del u, u squared del u, that exactly mimics this combination. And then now we replace this expression in the charge with this new expression at the price of having an infinite coefficient.
Okay.
And that's what we have in here. So this is just a manipulation to pull out the infinite piece from this apparently innocent looking charge.
So in their paper,
Yes.
Miguel Campiglia and Alocada, they had already shown these equivalents with the
Yes. So
root corrections, and they had these charges. So comments on.
yes.
On
So
the
the question they asked was, can there be a charge whose conservation equation, whose Ward identity gives you the logarithmic soft theorem? Now, what we are fishing for here is where do these charges come from? And what we are stating is that these charges actually come from just the covariant phase space analysis of the tree-level asymptotic symmetry, but now using fields that take into account long-range interactions.
But didn't they already include long-range interactions? They had this dressing with the massive particles.
Yes, they had the expression for the charges and the fall-offs. What they were missing was the covariant phase space analysis. So if you look at that paper, the question you'd have is, okay, so we have charges, we have the interacting fields, but where do these come from? Like, what symmetry gives you these charges? And that's what we are trying to answer here. Does that answer your question?
I suggest we let Sangmin continue and get back to at the end of the
Okay, one peculiar thing is that this del u squared del u is the operator, the projector that picks out the coefficient of log omega in the Fourier space.
Is there a log omega in Fourier space? I mean,
Sorry?
is there a log omega in Fourier? I mean, in the sense that if you
yes.
have integrable functions, then you shouldn't have log omega.
Yes, so this soft charge, if in computing the ward identity, the role this plays is that it inserts a soft photon to the amplitude and then takes the limit as the energy goes to 0 with a projector that picks out log omega. So what it would do is in this amplitude, it would have a projector that picks out this coefficient of log omega.
But are you saying that it picks out, what I'm not clear is, are you saying it picks out a log omega component in A naught? Or
Oh no, it picks out the log omega component of the amplitude
of the
as the energy, soft energy goes to 0. Yes. So collecting the two terms, we have log of the infrared scale times these two charges, and this charge was already derived by Campiglia and Lada, and it was shown that its ward identity gives you the log-soft theorem. So here's how it works. If we write down the ward identity, it turns out to be rewritten in this form, where we have log of the infrared scale plus finite corrections. So it looks divergent, but if we divide both sides by log omega inverse, then that gets rid of the finite piece, and what remains is a projection on the amplitude is equal to the log-soft vector times the amplitude without the photon. And this is exactly the divergent large gauge transformation. Its ward identity is the log-soft theorem. Now that was for QED. There's a similar story that runs in gravity. Schupo rotation charge takes the following form. It is formally divergent. There's a divergent term that goes like log of the regulator. There's a new term that you don't see in QED that has to do with the gravitational drag of the soft graviton. So what happens is that the hard particles now pull back the soft graviton, and this gives you a new term that is very reminiscent of what you would expect from something like Shapiro time delay. These have to be treated carefully. This is some detail that we are still working out, and we hope to put out soon in the next paper. And what that shows is that the ward identity of Schupo rotation is the log-soft graviton theorem. So to summarize, what we have shown is that it is the divergent large gauge transformation in QED, or BMS Schupo rotation in gravity, whose ward identity gives you the logarithmic soft photon and graviton theorem. More precisely, if you compute the ward identities using free fields, you'd get the tree-level subleading soft theorem. But if you now consider interactions seriously, then that The same order identity gives you the logarithmic soft theorem. So the asymptotic symmetry that gives you the tree-level soft theorem is the one that, again, gives you the logarithmic, the loop corrections once long-range interactions are taken into account. So that is all I have to say. Thank you.
So, do you want to follow up?
No, I want to open the file.
So, Sangmin was actually early on the, so we have time for questions.
I'm always a bit confused about these divergent charges. You said you used covariant phase space techniques to
Yes.
derive them. Do they follow from a finite, well-defined action or symplectic form?
Oh yeah, the action is completely fine. It's the symplectic structure.
But that's
That is
divergent, right?
Yes, that is divergent.
Okay.
Even before considering the divergent gauge transformations, the symplectic structure itself is divergent due to these new fall-offs.
Yeah, I
Yes.
would, but okay.
Yeah. Regarding that, so there is another. So I mean, even for tree-level subleading soft photon theorem, there is another proposal different from that of Campiglia and Lada
Yes.
by Pucci and Mao and I don't remember another postdoc who was in Brussels,
Yes.
where they say that the relevant charge you get. So when you do you just consider finite superphase rotations,
Yes.
and then the charge you get you can expand in powers of r,
Yes. Yes.
and then the leading term, which is finite, gives the leading soft photon theorem,
Yes.
and you have a subleading piece, which is the same charge that Campiglia and Leda wrote.
Yes.
The advantage of their approach is that you get everything from the same large gauge transformation,
Mhm.
and that I mean, from a phase space perspective, everything is finite.
Yes. Actually, so you were talking about this matching condition sort of way to approach.
Not matching condition. I'm just There is another paper.
I think they would use radial gauge or something.
I don't remember the details, but I like their approach because it's. I mean, everything is finite.
Yes.
Yes.
So this way of looking at things from the divergent phase space way of things. Well, I say divergent phase space, but phase space is not supposed to be divergent. So there should be a way to project all of. So I think this is a nice way of looking at things. But at the end of the day, I think there should be an equivalent way to project everything down to some finite phase space. Even maybe the price that we pay for doing this is we could lose some simple transformations. The transformations may be something very different from a large gauge transformation. For instance, in QED, we have the divergent phase space, but in gravity we don't. The phase space is very well defined because superrotation is not a divergent, quote unquote, transformation. There's some other ways to look at the QED, like the subleading transformations in QED that was developed in this UCLA group by Perkraus and others. There, everything is finite, but the transformation seems non-local. And maybe this is what happens in QED, not in gravity. But I think this is maybe the price that you have to pay to write down a finite phase space. But now the transformations are not simple gauge transformations, but they're something complicated, maybe non-local. And maybe this also has to do with the non-universality of subleading soft photon theorem. But this is just a speculation. But I agree that it would be nice to have a finite symplectic analysis. And maybe there's a way to achieve that from this point of view, but there's still more work to be done.
Yeah. Okay.
Quick remark if you want.
No. Yeah. I'm just saying. I mean, you say it would be nice, but this has been achieved for tree-level subleading soft photon theorem. It's just that people have largely disregarded it. But I think it's worth looking into. And it would be nice to maybe look at the loop corrections from that perspective.
I'd be happy to talk about this after. Yes, thank you.
Let's thank Sangmin Choi.
Thank you.